Okay. Good morning, everyone. My name is Calvin Atiku, and I'm a rising sophomore at the College of Engineering and Computer Science. I'm a mechanical engineering student, and I have a strong passion for materials engineering as well as entrepreneurship. Um, so there's currently a defect in engineering designs, and with this research, we may be able to improve these designs through referring to nature. I got involved with this research to follow both my passions and possibly create a business with the study. Now, to introduce my research, geckos are famous for their abilities to, for their super abilities to scale vertical walls and even hang upside down. Their toe pads are sticky and known for having one of the highest density among the animal kingdom. Each toe pad has a unique plays a critical role in adhesion. However, it is still unclear why geckos have such high density and such unique toe pad geometries. In this research, I present to you a framework of systematic designs of adhesive pillars, shapes, and compare each adhesive pillar to test their performance to understand how the tiny hair structures on the gecko feet can reach high strength. Using our study of adhesion, we plan to strengthen adhesive properties and develop a product that can be applied to the main structures of construction. AutoCAD and Fusion 360s were one of the main platforms I used throughout my 8 weeks in this program. I generated over 20 different design shapes through AutoCAD Inventor and compared their maximum stress distribution on Fusion 360. So basically, I compared their maximum stress distribution to understand how a gecko-like hair-like pillar can give a different response to other pillars' load of force. So what you can see right now is there's three of my main designs, which I have 20 throughout my research. The surface of each pillar was obtained by revolving a profile curve that is mathematically defined by the spring function on AutoCAD, going through different coordinate points. This means that the design phase will begin with a 2D isometric pillar shape. Then I use the spring function to draw. Mouse. I use the spring function to pretty much draw a curve from a specific point, for example, from R2 to R1. Next, I revolve the structure 180 degrees or 360 degrees from a 2D image to a 3D image. Here are just three examples of the pillars I said before, and this process was obtained. This process was obtained to help us diverse shapes in a consistent way and help open more opportunities for comparative. Now, we conducted find an element on each pillar by connecting 2 points and applying a load of 50 pounds upwards. That's why you can see the arrow point upwards. So through FE find an element method, we compare the maximum stress and their location for different pillars to understand how a gecko-like structure could give different response and other other pillars' load of force. With a different curve on each pillar comes a different one mass for mass stress and a normal stress distribution number. So I keep talking about one mass stress distribution and different stress level. So pretty much one mass stress is applied on each pillar to predict the yielded on each materials under complex. According to the one mass stress, failure occurs in the pillar when the energy of distillation reach the same energy for yielding. This is the primary reason why no point in the pillar must exceed the maximum stress distribution. So throughout our whole experiment, our result demonstrated that an adhesive pillar with a slightly small stress distribution shows the highest strength rate and makes the pillar stronger to avoid failure from the internal region. But maybe only if we take the adhesion interface into consideration. Our results found that design number 8, that I designed on AutoCAD, had the smallest one mass normal stress distribution level. And when applied a load of 50 pounds upward, it came up with a stress distribution number of 0.3023, making it the safest pillar among everything I designed. Design number 1, 3, and 9